Civil engineering relies on our ability to predict how structures behave under stress. Specifically, the branch of structural analysis allows us to calculate exactly how a beam will resist loads and deform over time. A beam subjected to a constant bending moment bends into a perfect circular arc, defined by its radius of curvature, r. Looking at the formula on the right, flexural rigidity, or EI, represents the beam's inherent resistance to bending. When the ratio of EI to the moment is constant, the radius remains constant, resulting in that perfect arc. To calculate the exact shape of that curve, we use the core engine, the differential equation of flexure. We integrate the bending moment equation once to find the slope, generating constant C1. We integrate a second time to find the deflection equation, generating C2. We then use physical boundary conditions to solve for those two constants. Double integration is the mathematical foundation of beam mechanics. However, in a timed exam setting, it has a major vulnerability. Every time a new load acts on the beam, the math fragments, making it a liability for complex problems. The failure point of double integration happens the moment you add a second load. That new load creates a new section of the beam, forcing you to write a separate bending moment equation and generating new constants, C3, C4, and so on. The algebra quickly spirals out of control. This comparison table shows how Macaulay's method solves that exact problem. Instead of splitting the beam into parts, Macaulay's method provides a way to write a single continuous bending moment equation for the entire beam, no matter how many point loads are on it. The friction point of this method, and the reason it works, is Rule 2. When evaluating the Macaulay bracket, if the term inside evaluates to a negative number, you drop it completely. You just equate the entire term to 0. By ignoring negative brackets, Macaulay's method turns off sections of the equation that don't apply yet, neutralizing the threat of multiple loads and keeping your math confined to just two global constants. We can also bypass the algebra entirely using visual techniques. The moment area method is highly effective for cantilevers and symmetrically loaded beams. First, you draw the M over EI diagram for the beam, which for a uniformly distributed load forms a parabola. Mohr's theorems give us the rest. The change in slope between 2 points is simply the net area of that parabola. To find the total deflection, you take the moment of that area, meaning you just multiply the area by the distance to its centroid. Our final tool is the conjugate beam method. It relies on a mathematical analogy. The calculus linking load, shear, and moment is identical to the calculus linking M over EI, slope, and deflection. To exploit this, we create an imaginary conjugate beam and load it with the M over EI diagram from our real beam. Because the underlying math is identical, the solution is procedural. The slope at any point on the real beam equals the shear force at the same point on the conjugate beam. Likewise, real beam deflection equals the conjugate's bending moment. Let's test this. Pause the video and try to sketch the conjugate beam and its loading diagram for a simply supported beam with a single central point load. Here is the solution. Your conjugate beam remains simply supported, but it now carries a triangular distributed load pointing upwards, representing the bending moment of the real beam. Mastering the moment area and conjugate beam methods allow you to skip calculus completely. You are transforming complex integration problems into basic statics problems, relying only on shear and moment calculations. We can apply these methods to statically indeterminate structures. Take a standard cantilever sagging under a distributed load and add a rigid vertical prop. That prop pushes the free end back up until it is perfectly level with the neutral axis. To solve for the unknown force of the prop, we use the principle of compatibility. The downward deflection caused by the distributed load must be perfectly equal and opposite to the upward deflection caused by the prop. They cancel out to 0 at the tip. In advanced problems, we encounter supports that are not perfectly rigid. If the prop yields or sinks by a specific amount, denoted here as delta yield, the beam settles below the neutral axis. The logic remains the same, we just adjust the math. The downward deflection from the load minus the upward deflection from the prop now equals that exact yield amount. You set up the equation and solve for the true prop reaction. This table summarizes the standard cases: cantilevers, simply supported beams, point loads, and distributed loads. Memorize these formulas. In a competitive setting, you do not have time to derive the maximum slope of a standard cantilever from scratch. True exam speed requires a dual approach. You must instantly recall the standard cases from this table to save time, but you also need a deep understanding of Macaulay's, moment area, and conjugate beam methods to deconstruct the inevitable trick questions.